When atoms are heated up, they can act in a way a little bit like black bodies in that they can emit light. And this is something that gives rise to something we call emission spectra. And these have been studied for quite some time and known for quite some time. But one of the things that's kind of peculiar about them is that under classical physics, we would expect maybe that a continuum of different energies might be observed in these emission spectra. But instead, what has been observed, and this is true even before the time of Planck and the use of photons and little wave packets for black body radiation, is that you might see a spectrum that looks something like this. Okay, for the hydrogen atom. All right, and this means that there are only very specific frequencies of light, the ones shown here, where light was emitted. And this was something that I think was not very well understood or explainable under classical physics. But we need to figure out why it is that atoms only emit at certain discrete frequencies. Okay, so these are called line spectra because they only have very certain discrete lines. And they must come about because there is an energy change that occurs in the matter that emits the light. So the atom emits light, it has to lose the energy that it emitted. And now that we have a way of quantifying the amount of energy that's coming off in the emitted light, in other words, each photon of light that comes off is carrying this much energy, that means that we can relate this, if you will, to the change in energy that happens when the atom emits the light. So, for example, the atom emits the light, it loses this much energy, so between this much energy and this much energy, and this can be related to the energy of the photon, which we have written as h nu. All right, so this is describing something that is hard to explain if matter can have any energy whatsoever. In fact, it suggests that only certain energy increments are allowed when atoms emit light. Okay, one way you can think of this is it's sort of the difference between a ladder and a fire pole. Okay, if you're on a fire pole, as long as you don't mind grabbing the pole very hard, you can slide down any amount of distance that you want. There's nothing that interrupts that. But with a ladder, you're constrained to going down in very discrete steps, certain amounts that you can go down that ladder or go up that ladder. So the ladder, if you will, has discrete increments, whereas the fire pole has continuous increments. So this would be what we would expect under classical physics, but the latter is what we actually observe. So in this way, we're beginning to see some phenomena that are different from what we expect from classical physics. Now, in the case of the hydrogen atom, there was an observation. There's a part of the hydrogen atom emission spectrum that occurs in the visible part. So this is the visible part of the spectrum. Okay, and there was a Swiss fellow named Balmer who around 1860, was able to look at the lines that were emitted by these, it was emitted by this hydrogen, and relate the frequency, and I'm going to use red again so that I can highlight this, relates the frequency of those lines in the following way. It was a constant times 1 minus 4 over n squared, where the n could equal 3, 4, 5, and so forth. All right, so in other words, this was an empirical model that allowed Balmer to predict exactly where these frequencies were, and this accounted for all of the lines in this visible region of the hydrogen atom emission spectrum. All right, as an empirical result, it was great, and it's interesting that it was very simple in its format. But the problem with that is that being an empirical formula, it did not explain why this was. And in fact, that was going to take some time to do. We're not going to actually talk about why in this particular video. But I'll point out that the visible part of the spectrum is just one piece for the hydrogen atom. That, in fact, if that visible part of the spectrum were here, so I'll reproduce it there, there's another piece of it that's up here at even higher thing. There's another piece that's down here that's a little closer together, another piece here, and another piece here. So you'll see that what's happening is that we've got different parts of the spectrum in hydrogen that have very similar bunchings of lines. In fact, we can call these clusters of lines. And this was the cluster that Balmer had observed. So this is in the visible part of the spectrum, and is now called the Balmer series of lines. This one up here is now called the Lyman series of lines. This next one is the Paschen series, and so forth, named after the people that studied them quite a bit. All right, but even though they studied them and so forth, we still didn't have a very good explanation for this, nor any relationship between these different lines. Well, this is where Rydberg came in. And what Rydberg did was he analyzed all of these lines. So he analyzed the patterns that appear here, and he found that, in fact, there was a self-similarity to these spectral lines, to these emission lines that occur in the hydrogen atom. And that, in fact, I don't know how he did it, but somehow he was able to figure out that you could model all of these lines, and I'm going to change this new to tilde, but you could, and I'll explain what that means in just a moment, but you could model all of them in the following way, that they were equal to this kind of relationship, where this R is a constant. These n's are both integers, and I'll say that, for example, n1 can equal 1, 2, 3, and so forth. n2 must be greater than n1. Okay, so it can be anything that's greater than n1. And these would tell us where these lines are in the spectrum. Now, in this formula, this constant here is something called the Rydberg constant. You see, if you discover something, you get to name it after yourself. So the Rydberg constant is a quantity that has the value of 109,737, and it's in units of inverse centimeters, okay, which is a unit that we also sometimes call wave numbers. Okay, and these wave numbers are a way of measuring the inverse wavelength of the light. Okay, now that's what defines this thing nu tilde. So nu tilde is essentially 1 over the wavelength of light in this, and is always going to have units of 1 over distance. Now, you can justify this, I suppose, if you look at the expression for the light of a photon is h nu, that this is also equal to hc over lambda, as we defined nu and lambda before. Remember, the product of nu and lambda is equal to c. So this nu is 1 over lambda. So, in other words, the energy of a photon might be equal to hc times nu. So anytime you want to go from wave numbers to energy in joules, you need to multiply by hc, the Planck constant times the speed of light. All right, let me continue this on a new page. Okay, so this energy conversion, so if we want to convert nu to, in wave numbers, to energy in joules, we would need to multiply by hc. Well, hc, when you multiply it together, has the value 1.9864 times 10 to the minus 15 joule meters. Or if you were to write this, I'm sorry, not minus 15, it's minus 25. Or if you were to write this in wave numbers, it would be 1.9864 times 10 to the minus 23 joule centimeters. All right, so this is your way of converting energy units. I want you to note, though, that when we're talking about energy transitions due to emission of light or absorption of light, there are several ways that we tend to measure this, and you'll need to be able to convert between them. So, for example, you can measure the energy just by declaring what is the frequency. Now, that's in inverse seconds, but we sometimes call inverse seconds hertz. Okay, or megahertz would be 10 to the 6th hertz. We also can measure energy in terms of these wave numbers, and we've already seen that they can be expressed in inverse centimeters. It's also sometimes possible to express them as inverse meters, but more frequently as inverse centimeters. And then lambda, the wavelength of light, and this is often used to describe the energy of light. Sometimes it is declared in units of meters, although it's usually a small number of meters. Could be declared in units of centimeters, micrometers, or even nanometers. Okay, so lots of different ways you can do this. Now, how would you convert these all into joules? Well, in the case of nu, you would multiply by Planck's constant. In the case of wave numbers, you would multiply by the product of Planck's constant and the speed of light. In the case of lambda, in case of wavelength, you would divide the wavelength into the product of Planck's constant, the speed of light. So all of these are different ways you can express energy transitions that occur spectroscopically. And the Rydberg formula that we've shown on the previous page back here, this Rydberg formula is one that is a rich source of problem material in a course like physical chemistry. So you may want to pay attention to it and know how to apply it in real problem solving cases.